This video builds off of a previous video I did with a basic wheel image carousel. If you haven't seen that, I'll have a link in the description below or a card on the top right. And so if you haven't seen that video, I don't go over that code in this video here, or this video will be another 45 minutes longer. So you need to see that video before you check out this video. Anyway, so what makes this carousel so advanced? Well, in the old carousel, when we rotated the wheel, the images rotated with that wheel, and so the images would appear upside down. We've now equalized or maintained the functionality of an image staying upright. Also, most importantly, we've introduced snapping points. So currently we have a snapping point at 90 degrees right here. We're going to rotate the wheel. Whichever card lands closest to that 90-degree mark, the wheel carousel automatically rotates and makes that that card more prominent. So let me just spin the wheel. So as you can see, whichever card lands closest to that 90 degrees, all the other cards shrink. That one stays the same, and we give the user some feedback as to which card is the selected card, or the image is the selected image. Anyways, if this interests you at all, stick around. Let's begin. So let's begin by replacing this div. We're going to be using images. We're just going to use an image tag, not a div. Let's get rid of this. Let's give this guy to an image. So we're going to need an alt. Just going to say OK. We're going to need a source. We're going to bring that through the this.props. We're going to convert this guy into a class. So it's going to be this.props.pick. And we're going to keep these styles. It should be self-closing like this. And let's just do this to clean it up a bit. There we go. There we go. Here we go. And here we go. All right. So we're taking in an image. It gets its source from this.props.pick. Let's add that to the wheel. So we're going to add a property called pick. And that's going to be equal to. And let's do this. So we need, I have a bunch of picks stored in the folder here. Should be in public, all these guys here. So we're just going to use that format. The tildes, we're going to say the I, so 0 through 7 right here. 0 through 7. It's going to be dash 200 by 200.jpg. Save, let's go back to the card. And modify these styles. This is going to be 200 pixels by 200 pixels. And we want a perfect circle, so the border radius will just do 50%. Let's see what we get. Save, go back. Props undefined, of course. We need to convert this guy into a class. So let's get rid of the function part. Class card extends react.component. We don't need this prop stuff. We need a constructor. Let's do that. Chord, get chords. We need a render here. Render. Put all this in here. Put the chord in here. And all these props data needs to be this.props. This.props. Let's say this.props. This is also this.props. And this.props. And this function here, let's put it in the class. So take that out. Put this here. No longer a function. We'll do an arrow function. All right. Get chords. This should be this.get chords. Does it look good? We don't really need this state. Get rid of that. Then it would make it obsolete. All right, we'll keep it. All right, class card. Save, go back. We need to increase the radius. So let's go to the wheel and the radius, which is right here. Let's make it 250. See if that looks better. Perfect. Let's also increase the radius of this this center guy here, that center div. So 200 by 200 as well. 200 and a border radius of 50%. All right. And finally, let's memoize the card. All memoize does is when we re-render the parent, which is this div here, this parent right here, this div. If you re-render the parent, the children, all the cards, the images, they automatically re-render as well. This is inefficient. So memoize says if there's no state change in any of the children, don't re-render the children. Just use the previous render. It's just a way to make more efficient code. So react.memo. And card. All right, so we converted to class. We have all these. Good to go. Get chords showing up on the screen. We changed these styles for these guys. All right. Now let's do a bit more cleanup before we actually move to the bulk or the major parts of this this video. Right now the wheel, the scrolling is based off of radians. I want to convert this to degrees because it's just easier to think about this stuff in terms of degrees. So instead of this line here, we're just going to say let scroll. Let me move this down here. Let's scroll speed equal that event equal event dot delta y divided by 360 degrees in a circle, and we're going to speed that up by 20. And we're just going to say temp theta plus equal to scroll speed. And instead of all these guys here, we can take this away and just do this dot temp theta. We also want to, what's going on here? This dot temp theta degrees. I got rid of, there we go. We also need to add some sort of transition properties for the wheel that we're going to need later. I'm just going to say this style dot transition duration TION is equal to 0.0 seconds, and the transition delay also equal to 0.0 seconds. So let's solve one piece of this puzzle. So currently when we spin this wheel, the images spin as well with it. So they go, they're upside down right now. We want these guys to keep upright. So how we can do that is we're just going to spin the images in the opposite wheel, or opposite direction of the wheel. So we're going to loop through the images here. Let me just do a, let's say maintain image equilibrium. Let me scroll up just a bit. All right, so we need a for loop. For let I equal 0, I is less than this dot wheel dot children dot length, I plus plus, and we're going to need this. So this dot wheel dot children of I and dot transform, and we want to maintain the 50-50 translate. So it's going to be equal to translate -50, -50. We want to add the rotate. So just like this guy up here. So rotate, there we go, and it's in degrees. So it's going to be the opposite direction of the rotation of the wheel. So we just do a -1 times this dot temp and theta. And we also need the transition stuff. So paste to paste, no longer the transform, I need the transition duration. I spelled it wrong. There we go. Duration, there's no I there, equals 0.0 seconds, 0.0 seconds, and transition delay, 0.0. All right, let's see what we get. Spin the wheel, and the images are not staying. Why is that? That's because we're missing a word. This would be style.transition. Style, and of course, style. STYLE, save, go back. All right, so there we go. The images are staying upright. So that's 1/3 of the puzzle. So now let's handle a bit of the snapback logic. And what I mean by that is, let me just refresh the page. All right, so when you spin the wheel, let's say we had this as a snapping point. So not this card exactly, but where the card is, so 90 degrees. So we spin the wheel, whichever card's closest to this 90-degree point, the wheel's going to automatically rotate to that point. And so once we've stopped rotating the wheel manually, we want it to snap back to that point, but not instantly. You want it to wait a bit and then snap back. It just looks better. Let's go to the code and implement the basically a way to call that function. So down here, once we've scrolled and we stop scrolling, this timer sets off. We want to call a different function. So we're going to set the temp to theta, and we're going to call a snapback function that we're going to write a bit later. So let's just say this dot snap back. There we go. Let's define it here. Snap underscore back, arrow function. All right. So we need to know when we're snapping and when we're not. So let's include another variable in the state called snap in progress. Set that false. Should be a colon, not an equal. And we go back down here. And so once we have stopped scrolling, we set the timer. It sets off. Theta is going to be equal to that theta, so we can keep up with where the wheel is, and the snap in progress should be set to true. And then we call the snap back. Then we go in here, and then we're going to have snap in progress set to false after we've done the snap logic. Another piece of logic that kind of fits in with the snapback logic is a loading logic. We're going to have to take some information from these cards, but we want to make sure that all the cards are loaded. The images of these guys here are loaded before we do that in the parent. So we need to build some sort of mechanism to do that. So we're going to have a function called, we'll say, I don't know, card underscore loaded equal, and we're going to pass this to each card right up here. Let's call it am loaded. Am loaded is equal to this dot card loaded, and we're going to go to the card. We're going to say component did mount. Component did mount. As soon as you mount, just call that function. So this dot props dot, I think it was am loaded. Am loaded, card loaded, perfect. So the logic behind this is we're going to increase the number of actually with the keep track of it. So another variable in the state called cards underscore loaded is equal to 0. Each time a card, a child loads, you want to increase that by 1. And once they're all loaded, which is 8 total cards, then we'll start then we're able to rotate the wheel, but not before. So we're just going to say this dot set state, and we want the card, we want the previous state. So previous state, arrow function, and we're going to do some stuff after, so let me just write that here. Another arrow function. All right, so we're just going to say the return an object, and that is the card loaded. Card underscore loaded is equal to the previous state dot card loaded plus 1. And the logic we're looking for is if this dot state dot card loaded, card loaded, is equal to the total number of cards we have is 8. Is equal to 8. That means we know we have all the children loaded, and we'll do some stuff here. We're going to set this dot set state, and we'll do this loaded. So we need a variable to keep track of whether or not we're loaded is equal to true. This dot set state. We don't need the thing there. So let's put that up here. Card loaded and loaded. So when we're loaded, set to false first. We'll set that to true, and then we can start scrolling. So let's build that into here. We're going to say if we're not loaded, so this dot state dot loaded is equal to false, then we're just going to return, else we're allowed to scroll the wheel. So we're allowed to do this snapback and all this action. Also that snap in progress, if we're in a current snap in progress, we also don't want to be able to rotate the wheel. So we can add that in here as well. And this dot snap in progress is equal to false. No, is equal to true. So if we're either not loaded, or it's not either. It's if we're not loaded and there's a snap in progress, return, else we can do all these this stuff here. Save. Let's see if you broke it. Spin it. Actually, let's do this. Let's do an alert in this guy. Alert. Snap. Rotate. Alert. There we go. All right. So the logic looks good. And delete that. So now that we know or give an indication to our program when to call the snapback function, let's write that actual function. And so what we're going to do is we're going to take one of these cards, and where the card is, not the card itself, is going to be the snap point. So let's say we took this card right here. That's a 45-degree angle. That's going to be the snap point. Any card that moves towards or stops is closest to, that 45-degree angle. The carousel, the wheel carousel, will automatically fix to that position. So how do we calculate what degree or where the snap point is? That's where a bit of trigonometry comes in. So let's say we had a snap point here that's 45 degrees, but we don't know it's 45 degrees. How do we calculate it being 45 degrees? Well, if we have a triangle like this, and the angle theta is right here, if we know theta, so tan of some theta is equal to y over x, but we don't have the theta. So we can take the inverse of this function, tan to the negative 1 is equal to, tan to the negative 1 of y over x is equal to that theta. So if we can get the y and the x, we know the degree or the actual snapping point. So we need to calculate two things. We need to calculate the center of this wheel, do an F5 here. So the center of the wheel and the center of any of these cards. So let's go to the code and actually do this. So let's scroll down here to the snapback function, and we're just going to calculate the center wheel first. So let center of wheel equal an object with an x and a y. And all the center of the wheel is the x and the y starts here at the corner. We give a border radius, but if this was a square div, the x and y is here. We need to take the x and y and then go half in x, half in y, and we get the center of the wheel. So we're just going to say this dot wheel dot get bounding client rect dot x plus half of the width of the wheel. So this dot wheel get bounding client dot width divided by 2, and for the y we just need copy paste. That's y. This is y as well, and that should be height. So we need to do the same thing for any of these cards, but we can't do it in here. If we do it in the snapback function, depending on where the card is, the degree is going to be off. So we just want, as soon as this loads up, these are the potential snapping points. 0 degrees, 45, 90, I think this is 135, 180, and so forth. So if we take that logic here and calculate the snapback, or snap point, snap underscore point here with another x and a y, like that, depending on where the images are, we're going to get different values for the snap points. We don't want that. As soon as this thing loads, that's when we want to calculate the snap point. And luckily, we have a function that gets called as soon as the children load, which is right up, handle scroll right up here. So as soon as this mounts, no, not right up here, when the children are loaded, there we go, card loaded. So when we've actually loaded all 8 cards, we want to add something to this, a snap point. And we'll do an x and a y, so same thing, we'll do this dot wheel dot children, and we'll take, let's say, this guy right here. I'll take this guy as a snapping point. That should be 90 degrees, so it's 0, 1, that's the second index, or the third card. So 2, and maybe get bounding rect, same logic, plus the half, so this dot wheel dot children 2 dot get bounding rect dot width divided by 2. Let's copy paste. That should be a y. Same 2. This should be a y, and this should be height. All right. So we have the center of our wheel, and we have the center of a snapping point, a card. And there we go. Let's add the snap point to this state up here. Just say snap underscore point, and it's just going to be an x and a y. Just say null and null. Now let's go back down and actually calculate that theta. So we'll go down here. We'll say I'll do it right here, let snap point theta equal, and we're just going to do that formula, the y over the x, and we'll choose the, what is it, 0, 1, the second index, third card. So y over x. There's going to be math.a10, 2, and we want the absolute value. We don't care about positive or negative. It's going to be the snap point. So this dot state dot snap point, y minus the center of wheels y, and all of that over the same thing. So math.abs, and this dot state dot snap point dot x minus the center of wheels x, center of wheel dot x, and this is in you could say radians if you want. Let's convert this to degrees. It's easier to think in degrees. So snap point theta times equal, and the formula for that would just be 180 over math.pi. Math.pi should convert into degrees. Let me save. So we have the snap point theta there. So now that we have the snap point theta, we want to calculate which card is closest to that theta. So how are we going to do that? So let's just say the snap point is going to be the 90 degree mark. We spin the wheel. How do we know which card is closest to 90 degrees? Let's do a bit more trigonometry. So let's say our snapping point is the 90 degrees. Nope, not there. Right here. Let's just say the green dots are the center of some images on the wheel. There's one there, there's one there, there's one there. So how do we know which one of these guys? Visually, we can see it's this guy right here. How do we know that this guy is closest to the snapping point? Well, we need to calculate the distances between the snapping point and all of these, the center of each image. And then we compare the distances. The shortest distance is obviously the closest card. So how do we get the distance between these guys in a circle? Well, a bit more trigonometry. So let's say we have the triangle like this. And we know the y, just like we knew the y when we calculated the snapping point. We know the x. How do we get this h, the hypotenuse? Well, what is a squared plus b squared? It's equal to c squared, the Pythagorean theorem. So let's just say we have the x squared plus y squared is equal to our h squared. We isolate for h. That's going to be equal to the square root of x squared plus y squared. So we're going to go into the code. We're going to perform this formula. We're going to loop through, compare distances. The shortest distance is obviously the closest card. So let's go back here. And I noticed an error in the code before. This card loaded. There's no card loaded. It should be cards loaded. So cards loaded and cards loaded. All right, so let's get back to the shortest distance. So we need an initial shortest distance so we can measure something against that. So we're just going to say let shortest distance equal, and this could get a bit messy, but we're just going to say this is going to be the x squared. So math.pow, something squared plus, this will be the y squared, something squared there. And then we'll say shortest distance equal to square root of that shortest distance. So let's fill in these guys. So the x squared is just like the theta. We take the difference between the yy and the xx. So we're just going to do, and it doesn't matter which card we take. We'll just do the third card, or the third index fourth card. We just need something to start with. Children 3 bounding rect.x plus half of that width. So wheel.children 3 dot, where are we at? Bounding rect.width divided by 2. And another bracket there. And of course, we need to know the difference between the two. So we need to do a minus. And this should be this dot state dot snap point dot x. Copy, paste, put a plus there. No, put a plus there, delete that. And this should be the y stuff. So, no, y there. This should be height. This should be snap point y. And we got the shortest distance. All right, so let's loop through all the cards and compare the shortest distances. So for let I equal 0, I is less than this dot wheel dot children dot length I plus plus. And let's break this up into separate variables. So dx is going to be equal to something, and let dy equal to something, and then we get the current, let's say shortest distance is equal to math.square root of dx plus dy. So what is dx? Well, it's just this guy right here. So we can copy this, put that there. And of course, it's not the third index, it's the I index. And this should be I as well. And we can copy this for the y. And of course, it's not 3, it's I and I. And let's compare the distances now. So if the current shortest distance is less than or equal to the shortest distance we're comparing it against, we obviously know that the shortest distance then becomes the current shortest distance. And let's save which card has the shortest distance as well. So let's say let closest card equal null. And we'll do the closest card is equal to whatever current card we're on. So this dot wheel at children of I. So let's print out all this stuff and see if we broke the program. So let's say console.log, give me the shortest distance. Give me the closest card first. Closest card, and give me the shortest distance. Shortest distance, and up here, let's say, give me the snap point theta, just so we know that this calculation went smoothly. Snap point theta. Save, the snap point should be the second index. So third card, 90 degrees. Let's go here. Let me get the console. Let's refresh. So spin the wheel. And let's see if we get the console. So 89.999, which is 90 degrees basically. And right here, that's the closest card by 90. That's not degrees, that's 90 pixels. Let's spin again, see what we get. And so the closest card is this guy right here. And it's a 15 pixel, the difference between the 90 degree mark, which is somewhere here, and the center of this card, which is somewhere here. All right, it's good. So it's working. Now that we have we know the closest card to the snap point, we need to know the degree. So let's say we rotate the wheel, the snap point's at 90 degrees. Let's say this guy's the closest card. We need to know the difference in degrees between the snap point, which is 90 degrees, and wherever this is. So let me just draw that out quickly for you guys so you know what I'm talking about. So let's say we have a snap point at 90 degrees. We rotate the wheel, and the closest image falls right here. How do we get this, the difference in degrees? Well, we calculate, we have 90 degrees right here. So let's just say this is the center of the wheel. The 90 degree snap point is all the way over here. That's 90 degrees. Let's say whatever this is, let's just say this is, I don't know, let's say 85 degrees. So 85 degrees all the way to here. If we take the difference between these two, we should get this guy right here. So let's go to the code and actually do this. And here we go. Let's get rid of these console logs. Delete that. Closest card is equal to no. We don't use it yet. All right. Let's go down here. Actually put some comments. So calculate shortest distance. And we'll say calculate theta between closest card and snap point. All right, so let's calculate we need the x's and the y's. So just like we calculated the snap point with the x and the y like this, x and y, and we use that tan -1 business. We need to do that again, but just for this guy right here. So we can copy and paste code and just modify it. So where did we get the x and the y of a current card? That was right here. Copy this right here. And paste. So let's say this one is let closest cards x equal that. There we go. And this is let closest cards y equal that. There we go. So just a quick correction I noticed when I was doing some editing. This line right here, I didn't modify it properly. So I copied it, but I didn't modify it. This shouldn't be this.wheel.children2. This should just be the closest card. So all these guys, closest card as well, closest card, and these guys as well. So we have the x and y. Now we can use that tan formula, this guy right here. Yank that, paste that here, and this should be not snap point theta, closest cards theta. Closest cards theta. And it's not the snap point minus the center of the wheel. It is, where is it? Closest cards. This is the y. So closest cards y minus the center of the wheel y. And this should be closest cards x. Closest cards x minus center of x, and of course this is not snap point theta, closest cards theta. And to get the theta, the degree difference between, we just do a simple subtraction. So let's just say let theta between equal math.add closest cards theta minus the snap point theta. All right, so we had the theta between them. Now I'm going to copy and paste an if-else-if structure. It's just way too much of a hassle to write it out. I'll explain it once I've copy-pasted it. All right, so what is this mess that I've just copy-pasted? Let's draw it first, and then I'll just show you what the code is. So let me just move over here. All right, so in a 2D coordinate system, we have the idea of quadrants. So this would be quadrant 1, this would be quadrant 2. Let me turn that off. It's annoying. All right. We have quadrant 3, and then we have quadrant 4. So depending on which quadrant we're in, we want to rotate the wheel a different way. So all this structure does is, so we know the difference in degrees, but it's in absolute terms. So it's always a positive. We want to know based on which quadrant we're in, if we want to rotate positive or negative in a certain direction. So all this structure does is say, if the closest card's x is greater than the center of wheel and the closest card's y is less than center of wheel y. So basically, if the closest card is here and the snap point is here, we want to rotate in the negative direction. This would be the negative direction. This would be the positive direction, I think. Or this is positive and negative. So anyways, all this structure does is, depending on which quadrant we're in, we have to tell the wheel which way to rotate in order to get the card, this guy right here, to show up at the snap point, because it's not always the same. The snap point's here and the card's here. We want to rotate in this direction, which might be a positive direction. The snap point is here and the card's here. Excuse me, snap point's here, card's here. We want to rotate in this direction, which is a negative direction. So that's all this is. It's a bit complicated looking, or just depending on the quadrant, we want to rotate positive or negative. So let's do this. So now we just need to rotate the wheel. And we rotate the wheel up here so we can just copy and paste a bunch of code. So copy all this, And this set timeout as well. Yank that. Let's go down here. And let me do some formatting and comment. So rotate or snap wheel to snapping point. So we're going to have a duration of 0.1, or else it's going to be really janky. This just comes out of experimenting with the values. We're going to rotate by this dot state, so the current state of the wheel, current rotation of the wheel, so this dot state dot theta plus the theta between that we calculated. And then we do the opposite for this guy, times, and let me just do this. There we go, this dot state dot theta plus the theta between. And of course, if we're rotating the wheel, we need to save that transaction. So we don't need any of this, so we're not calling anything afterwards. So we can condense this down into something like that. So theta is going to be equal to this dot temp theta. No, it's going to be equal to previous state's theta plus the theta between. Let's do this. Return that object and close you off. All right. And snap in progress, false, because we've already snapped it. And that's going to be equal to the previous state's theta plus the theta between. All right, that looks good. And we're going to wait 200 milliseconds here. All right, looks good. Let's see if that broke the program. So go back here, let's rotate, see what we get. All right, that was a bit weird. And why was that weird? Let's do this. 0.1 as well, and 1.0 as well. Save, go back, rotate, or excuse me, refresh, rotate. And that looked a bit janky. Why? These values are different. So this shouldn't be 0.1. That should be 1.0. This should be 0.1. 0.1. Let's change that here as well. So 1.0 and 0.1, and let's test it again. 0.1. Save, go back, rotate the wheel. We should snap towards, well, we'll take care of that later. All right, there we go. So the last thing we need to do is make this card larger and these cards smaller, or keep this one the same size and make these guys smaller so we know that this is the snapping point. So we just need an if clause structure in here. We're going to say if, let's say this dot wheel dot children, the current card is equal to the closest card, equal to the closest card, not closest card's theta, closest card, there we go. I'm going to do something here, else we're going to do something here. This is going to be the same. Oh, not that. All right, so we're going to add something to this. So if it's the closest card, we want to maintain the scale. So we're going to say scale of 1.0. If it's not the closest card, with a scale of 0.5. And we're going to change the Z index as well. So this guy is always on top of the other guys. So style dot Z index. And we'll just do 100. And for this guy, we'll do 1. So let's see if it works. So we rotate the wheel. The closest card to the 90 degrees should rotate back or snap back to it. It should, well, it's going to maintain its scale. The rest should shrink. So let's spin the wheel. All right, so it looks good. Let me spin again. Let's choose a different snapping point. Let's do the, let's go 0, 1, 2. Let's fix this third index or the fourth card. So let's go up here. Or is it down here? It is down here. Say 4. Let's put that in a separate variable so I don't have to make 4 different changes. Let me just say let snap point index equal 4. And we'll do snap point index. Snap point underscore index. There we go. There we go. Snap point index. There we go. And snap point index. Save. Go back. And so the closest card to this point right here should be the snapping point. So let's spin the wheel. Perfect. Spin again. Perfect. All right, so that's going to be it for the video. Leave a like, subscribe if you haven't already subscribed, and I will see you guys in the next one.